Okay, so if you remember last time we started talking about page replacement policies, and we gave you several of them. The first three were kind of base cases against which to measure. So FIFO is the obvious simple one where we just plain treat the pages kind of one after another as the replacement policy. This is good because it's simple, but it's bad because it doesn't distinguish between frequently used pages and infrequently used pages. So from the standpoint of a cache, it's actually a pretty poor replacement policy. Min is kind of a guaranteed not to exceed good policy that throws a page out only if it's going to be used as the furthest in the future. Okay? And then finally, random is when you got to throw out a page, pick a random page. Now, random was pretty good in the hardware case where the time to go to DRAM wasn't too bad. In the case of page replacement, unfortunately, if you throw out the wrong page, you got to go to the disk, and you take a million cycle hit. So we got to do better than random. All right, and so that kind of led us to LRU as sort of the simplest policy that's good to think about. And this is replace the page that was used the longest in the past. All right, and that's kind of, it's sort of an approximation to min, because if it's used the farthest in the past, it's probably going to be used the farthest in the future. Were there any questions about these replacement policies? Yeah. Well, min is not used. And nobody uses FIFO because, as I showed you last time, it's Bilaty's anomaly. Random, probably not. LRU can implement it. So the short answer would be maybe none of them are actually used in real operating systems. But they perform, basically, these are rulers by which we measure the policies we do come up with. Okay? It's a good question, though. And I do want to make sure we're in context here. Remember, we're talking about replacement policies, okay? Before we were talking about associativity and all that sort of stuff. All we're talking about here is when we have to throw out a page, which one do we pick? Okay? All right. So the clock algorithm was our first sort of reasonable and actually implemented policy we came up with. And the notion here of it being a clock is that you basically put all the pages in a huge ring. Okay, and then there's a single hand that's working its way around, so it's kind of like a clock with one hand. All right, and the first version of this, we'll talk about a couple of other ones today. Basically, you only advance the hand on a page fault. And what we're interested in is we're replacing, right? So what we're trying to do is figure out on a page fault, which page do we throw out? Let me ask you this. On a page fault, which page do we pull in? Yes. Yeah, good. The page you were trying to find. Yeah, so that hopefully is a dumb question, right? We know which page we're pulling in. The question is, which one are we throwing out, all right? I keep saying that because I want to make sure that sinks in. We're really interested in throwing pages out. So how does this work? Pages are in a ring. Basically, there's a single use bit that's in the page table entry. And what does the use bit mean? Well, it means when it's set to 1, it means the page has been used recently. Okay, if it's not set, it means it hasn't been used recently. And the thing to keep in mind here is that typically the use bit goes from 0 to 1 because the hardware sets it from 0 to 1, and it gets from 1 to 0 because the software sets it. Okay? So what is our basic idea here? On a page fault, what we do is we advance the clock hand to the next page. We take a look at its use bit. If the use bit's a 1, we say, oh, this page has been used recently. Don't bother it. If it's a 1, we're also going to set the use bit to 0 at that point because we're going to check the next time around whether it's been used. Okay? If, on the other hand, the use bit was 0, then it's an old page, and we can replace it. Okay, that's the simple clock algorithm. Were there any questions on that? Yeah.
If we're doing this every page fault, shouldn't we have a page fault where we don't
Yeah. So what we're assuming here is that we're at the steady state where all the pages are used. Okay, and we have to find a replacement page.
So you don't actually run the clock algorithm until all the
Yeah. In fact, we don't even quite do it this way. I'll show you in a moment when we add a free list onto this. Okay, and it'll be probably closer to what you're thinking. But let's assume for the point of this right now that every page is in use, and our whole task is to pick one of the pages to throw out so we can bring our new page in. Okay? And notice that this is an approximation to LRU. Why do I say that? Because it divides the pages into two categories, those that are active and those that are inactive. Not the least, we can't find the oldest page here, or the least recently used page, excuse me, because we don't have that information, but we can find an old page. That's the key. Okay, good. Any other questions on this? Okay, so the use bit goes to 1 when the hardware notices that you load or store from a page, and the software sets it to 0. So keep that in mind. Okay, now the other thing we talked about is the nth chance algorithm, which is basically a generalization of the clock algorithm. Rather than dividing pages into two pieces, old and new, we divide them into multiple chunks. In fact, you could say that we divide them into kind of n+1 chunks. Okay, and the basic idea here is the operating system in software somewhere keeps a counter per page, which is log n in size, basically. And on a page fault, the operating system does very similar to what we just said. It says, oh, is the use bit set? If it's set, we know it's a really active page. Why? Because it's been set in one clock period. Okay? So in that case, what we do is we just clear the use bit and clear the counter, and that's our category of extremely active pages. Now, the only thing that's different here is if the bit is 0, we're going to give it more chances before we throw it out. So when it's 0, when the use bit is 0, at that point we increment the counter, and only when the counter hits n do we decide to throw this page out. So notice why we're calling it the nth chance is we're giving it n loops before we declare it old enough to throw out. Okay, so that's the only difference here. And how do you pick the right n? Well, as n gets larger, you kind of get closer and closer to LRU because you've got more and more chunks of pages, right? You've got really recent, less recent, and so on, all the way till really old. Okay, so if you have zillions, if n is really big, then you get LRU, but it's extremely expensive. Why? Yeah, you got to go around many, many, many times sometimes to find an old page. Okay, so that would tend to say you want small n. Now, I gave you one example of a use of n, which is very simple, which is n is 1 for a page that's not dirty and 2 for a page that's dirty. And the whole point of that was if you're going around the clock algorithm and you find a page that hasn't been used in the last cycle but is dirty, at that point you start it getting written back to disk, and then if you come around and it's still not used, then you know that you can use it because it's been written to disk. Okay. So those were most of the algorithms we talked about last time. I started on the second chance list, but I'll redo that. So any questions? Okay. Good? So where does the counter go? So it's in software. So where? Somewhere in the OS. Okay? Remember I showed you a PTE from Intel that had 3 bits in the middle called OS? You could actually use the undefined bits in the page table in some cases to do a counter like this if you felt like it. Okay? Or you could have a completely separate array in memory. Okay. So today I want to wrap this up. And we'll talk about working set and thrashing, and then at the very end of the hour we'll talk about I/O systems. So the second chance list algorithm is a slightly different approach than the clock algorithm to approximating LRU. Remember, all we're trying to do is approximate LRU. And the history behind this is a little amusing. I told you this before, and I'll repeat it on the next slide. But the chief architect of the VAX, Streckler, came to the OS folks when the machine was being designed and said, do you need any special hardware support for the operating system? And one of the things they told him that they didn't need was a use bit in hardware. Don't need a use bit. Now, later, he was given a hard time, and people laughed at the fact that he didn't think to put a use bit into his hardware, but it wasn't his fault. Okay? But what did the OS folks do when they discovered there was no use bit? Okay? They did this algorithm instead of the clock algorithm. Okay? Can somebody give me a reason why they might not have wanted to use the clock algorithm without the use bit? Yeah. We'd have to store the use bit in software and actually produce it in software as well. So remember I gave you that hack where when the clock comes around, you set the page invalid, and then if anybody tries to use it, you get a page fault. You mark your little use bit in software and so on. Remember I talked about that? So we could make the use bit work in software, but this is sort of a better algorithm that has less page faults involved. All right? And what we do is we divide into two categories, a green category and a yellow category. And the green and the yellow category all represent pages that are actually in memory. They're not out on disk. Okay, so these are our active set of pages. But the green ones are marked read-write and are usable. And the yellow ones are marked invalid. So even though they have the right data in them, they're marked invalid. So they are guaranteed to cause a page fault. Everybody with me on that? And the way we manage these two things is very different. The green is managed in a FIFO fashion. So basically, the oldest green page is the one that gets kicked out when we put a new one in, purely FIFO. The yellow ones are managed like a linked list LRU algorithm. So this is software version that you might have designed in 61B to do LRU. Okay? So here's how this works. The active pages, you access at full speed. Why? Well, the hardware just lets you do them. Okay? Now, unfortunately, since there's no use bit, there's no way to know whether these pages have been used or not. So we just basically let the hardware use them. And the only time we ever kick a page out of the green side is if there's a page fault. Well, there certainly isn't going to be a page fault on the green side. There would have to be a page fault either because there's a page we want that's in the yellow category, or there's a page that's out on disk. Those are two cases where things are invalid and we might need to change the configuration. So, how does this work? Well, let's take a simple example of a page fault. So page fault, we'll start with one where the page fault is because the page we really want is over here. Well, first of all, since we're managing the green's LRU, we kick the oldest one into the yellow side, okay, and we're going to manage this LRU. So basically, this green one becomes the newest page in the LRU list, and the oldest one, of course, is at the top here. Is everybody with me? And now we take the page that we wanted to access, which caused our page fault, and we put it on the green list, all right, as the newest page, and mark it as valid. So this one becomes invalid over here, and this guy becomes valid. And because we yanked it out of the middle of the list and compressed, we still know that the oldest one of the yellows is up here, and the newest is down there. Okay? All right? And of course, if we got a page fault because the thing was out on disk instead of where we want it, then what we need to do is page in from disk to the active page rather than pulling it from the yellow guy. We'll have to kick a green one out over here, and then the oldest one at that point actually goes to disk. So if you think about this from an approximation of LRU, the approximation part has to do with when we page something in from disk, we try to page out the oldest LRU page. Otherwise, all we do is we shuffle pages among the two lists. Okay. Questions? Yes? Yep. No. So give me.
A page that's next to be kicked out, and I use it 10 times, and then I ask for a new page from disk, it's still going to move.
Yeah. So remember, the problem with FIFO algorithms is they don't distinguish frequently used pages from infrequently used pages. Can somebody explain to me why the green pages can't distinguish frequently used from infrequently used? Yeah. So first of all, the hardware has no use bit. Oversight. Second of all, because they're mapped, basically we're just letting the accesses go through. So we have no page faults and no hardware to tell us whether something's been used a lot or not. So it's purely FIFO. Well, the FIFO behavior is done because of the way we move things around. You know, we'll put a new page on one side and we'll kick something out on the other side. But it has nothing to do with how you access things in the green side. Okay, good. Yes? Well, this is a good question. How big is green versus yellow? That's kind of your question, right? So what happens if green is huge and yellow is small? What do we get? Yes? Looks like FIFO. What happens if green is small and yellow is large? Looks mostly LRU. And notice the trade-off in here is between efficiency of access with no page faults and how close you are to LRU. So you could imagine tweaking how big the two lists are based on what behavior you wanted. Good. Okay. So when the question was asked at the beginning of the lecture, which of those 4 algorithms I gave are actually used, you could kind of say that this algorithm uses both FIFO and LRU in a tunable fashion, maybe. Okay, and this is a real algorithm used in digital VAX VMS. Question, yes? Well, no, but see, remember when I said, the reason I said we couldn't actually implement LRU wasn't that you couldn't build LRU, it was that it would be too expensive. And notice that we're taking a page fault every time we touch the yellow page. There's always a page fault. So at that point, we're in for a bunch of instructions anyway. So moving some things around on a list is really kind of par for the course. Doesn't really affect us much. So I would say that this is actually LRU. This is not even an approximation. This is honest to goodness LRU. Yeah?
What happens if you want an active case that's just read-only?
Okay, so this is the simplest version. The question is, what if we really want something in the green side to be read-only? So bottom line, you could do that as well. It means that you have metadata outside of this process that keeps track of whether when you put something on the green list, it's read-only or read-write. You know, maybe some of those bits in that PTE or something. That's a good question. Okay. Are we good? Oh, one more question. Yeah.
So why don't they use an algorithm much more like the multi-level algorithm that you saw for scheduling, where you've got a really fast clock and a really slow clock, and you have the same clock as you want, moving at different levels of speed? Because it seems like you have memory usage patterns that are very similar to.
So you're not asking why we, on the VAX, they didn't do that, but why in the case of the clock algorithm didn't they do a multi-level algorithm? Is that what you're asking? Complexity. Actually, in a moment, I'll sort of talk about some variants on the clock, which aren't really multiple rings, but try to keep track of who owns what pages, and so you basically are only stealing pages from yourself versus everybody. But yeah, I haven't seen any multiple ring clock algorithms, if that's what you're asking.
Why is that so much more common for the scheduling and not for pages? You think the cost of page use is much more substantial at some point to get it right?
So I would say the reason that we haven't seen multiple clocks in the page case is I'm not sure it's demonstrably better on the one hand. And on the second, it's very complicated and there's a lot of pages. I mean, the number of pages in the system is huge. And if you've got to keep them linked into many levels of rings, it might get complicated and introduce bugs and stuff. So, whereas in the case of the multi-level scheduler, you have a handful of processes, handfuls 100 or 200, whereas pages you got, hundreds of thousands of pages, and so you could easily screw things up. That's my on-the-spot guess answer to why we haven't seen anything like what you're asking. Yeah. So there's kind of two classes of pages marked invalid in the system. There are ones that are actually in memory but marked invalid. And then there's ones that aren't in memory and marked invalid. And both of those, as far as the PTE is concerned, they're both the same level of invalid. I mean, it's that bits off. So the software has to keep track of whether a page is invalid because it's in the yellow list or it's invalid because it's on disk. Good question. All right, good. So you can see how hardware limitations can lead to completely different algorithms. I mean, this is, I would say, substantially different from the clock algorithm. I don't know what you guys think, but now, as we mentioned, kind of, if you have zero, oh, by the way, the yellow thing is the second chance list, as you can imagine. And why is that? Well, when we kick something out, we have a second chance to reuse it before we kick it to disk. I mean, you can see why that's called that, right? So, you know, if you have nothing in the yellow category, you got FIFO. If it's all in the yellow category, you got LRU, but you got a page fault in every page reference. Okay, so that's expensive. So you pick some intermediates. Okay, and you know, the pros and cons, few disk accesses. If a page only goes to disk if it's not used for a long time. And you've got an increased overhead with trapping to the OS in this algorithm over the clock algorithm native. But if, on the other hand, you didn't have a use bit, this is a lot less traps. So, basically, we're going to, you know, you've already seen, I would say later we'll talk about, but you've already seen some examples of different uses of page translation to do things like copy and write and so on. So we'll hold off on that. So, and again, why didn't the VAX use the use bit? Because Streckler asked the OS people, they said they didn't need it, and they didn't put it in. The VAX, by the way, did okay, even if we laugh at it because of its polynomial multiply. Okay. So let me show you something that's got a flavor of the second chance list. Okay? So one of the problems you could see with the clock algorithm that I gave you was that basically, gee, if every time you page fault, you got to walk all through this clock, that could be expensive. You know, page fault's expensive already. Do I really want to go to the trouble of running the clock algorithm at the moment I need a page? Wouldn't it be better if I had, say, a free list? Okay? And so most operating systems actually have a free list, which is a list of pages that are on their way to becoming free enough to reuse. Now, what I mean by that is when they're in the free list, they're still mapped. Okay? And so it's still possible to have accesses to them. Okay? Well, it depends on how you manage the free list. They could be unmapped, but in that case, I'd make them yellow. But the point is they're not out of memory yet. They're basically reusable. So from the time that we stick a page in the free list to when we use it, it's possible to kick it back in to the clock. Okay? The second thing to note here is that when I kick a page out to the free list, if it's dirty, I start copying it to disk right away. So by the time it gets to the head of the free list, hopefully it's clean. All right? Now, how does this algorithm work? Well, now the clock hand is actually independent of the page faults. And the clock hand only advances when I don't have enough free pages. So that's actually a background task. And you may have seen this background task, the pager. Anybody ever seen a pager daemon or something like that in their list of tasks? Well, that's something that's basically trying to fill up the free list with enough free pages by running the clock algorithm. Yeah, question?
So enough is like a constant number, like not just like one.
Yeah, it's a handful. And it's probably a tunable constant in most operating systems. But yeah, it's not one, it's a handful. Because you actually want to have time when you kick something into the free list for a dirty page to make it to disk before it gets to the head. So you need to have enough pages there to handle your page faults. Good question. So this is what the page out daemon typically is doing. Dirty pages copied to disk right away. And you could kind of view this as like the VAX second chance list, because if you need a page before it's made to the head here, you can actually kick it back in to the clock. Okay, so this is basically, the point here is to avoid paging out a page that's in use as much as possible. Okay, questions? Yeah. Yeah. So if it's in the free list and it hasn't been reused yet, then it's potentially, you can just kick it back into the clock, just like in the case of the yellow guys, we could kick it back into to the green side. Yeah. Good. Okay. So does a software-loaded TLB have a use bit or need a use bit? Okay, so there's a couple of options there. So remember, software-loaded TLB is exactly what you guys are doing for Project 3. So one option is the hardware sets the use bit in the TLB automatically, and then when the TLB entries replace, the software has to kick it back out to the page table. Okay, so this is a case where the TLB becomes dirty relative to the page table, and it's up to the software to write it back. And by the way, that's probably a case that you're going to have to deal with. Another option here is that the software is basically managing all the TLB entries as a FIFO list, and the way you get use is if something's in the TLB, then it's being used, and you kick it out kind of after a while if it's not being used. And so the TLB entry is always representing an in-use page. Okay, so this is kind of a way of getting a use bit, just because if it's mapped in the TLB, then it must be in memory. The last thing I want to talk about here is a core map. So page tables map virtual memory to physical memory, right? Is there any utility to go in the other direction? Why might you want to go the other way, go from physical memory to virtual memory? Yeah. So you're saying because it's easy to do, you might do it? Okay. I guess I'm asking, so I'll buy that there's far fewer physical pages than virtual pages. I guess the question is, why might you need to do that mapping? It's the question. Yeah. Yeah, so follow that thought. When we're doing demand paging, we're swapping something out. So how does that imply we might need a core map? Yeah, so if we're going to swap out a page, get rid of a page, we got to figure out which page tables it's in so that we can invalidate it. This gets particularly hard if multiple page tables reference the same physical page table, okay? And so that's kind of the idea of a reverse mapping. And basically the clock algorithm's marching through physical pages. Once you've decided that you have a candidate page and you want to kick it out, you got to go find all the page tables it's in to unkick it or to mark them invalid. Yeah, question.
So you're saying this works even with shared pages?
Yeah. So shared, in the case of the shared pages, there would be more than one mapping for a physical page. Yes. Question, yeah.
Clock algorithm is being applied on physical pages. Does the hardware have to know, like, in a special place where the physical page table is?
You mean to do the core map, or what's your question?
In order for the hardware to set the use bit,
Sure.
it has to know where in memory, presumably it's not setting use bits to all memory. It has to know where in memory we're keeping our listed physical pages.
It doesn't so much, because where are the use bits? They're in the page table entries, right? So basically, every time you do an access, there is a page table entry involved. And so, so basically, that gets set.
So it sets one of the use bits in one of the page table entries. We have to hunt down potential duplicates.
Yes, exactly. Well, that's one of the issues. The other is just hunting down other things when you're paging things out as well. So it's both to know what the use bits are and to know which page tables have to be changed when you page something out. Both of those are addressed by a core map. Good question. Okay. Any other questions? Good. Administrivia. So we're almost there on the midterms. There were some solutions posted. I don't know if you guys noticed that. We had a couple of minor fixes. I will put up an updated solution. There were a couple of typos in there, and I'll fix those. But by and large, the solutions are correct. We will hope to hand them out. Oops, I say tomorrow. I meant Friday. It's like tomorrow, but different. Okay. Of course, I mentioned that an extra 5% is what you get by attending lectures and sections and asking questions. Making sure your TAs and faculty know who you are is also useful. And we have anonymous feedback. I mentioned that last time too. I don't know if anybody's really used it. We have some terms where we get lots of anonymous feedback and other terms where we don't. So I guess you guys are all thoroughly happy with the course, and there's no reason for any feedback whatsoever. I will actually get a survey to you guys. Are you all comfortable with SurveyMonkey? I mean, you've used it a lot. If we were to, so I may actually put together. This may be the first term I try this, but I'll put together a survey, possibly using SurveyMonkey, which works pretty well. The alternative is physical paper, which I sometimes do as well. But why kill trees when you can kill electrons? So you should all be working on Project 3, although I know there are a few still working on Project 2. The auto grader is an intermittent thing in the early parts of a project. We had a few cases where people were saying, well, this doesn't pass the auto grader. I suspect those were because of complicated bugs, but you should be viewing the auto grader not as the way to test your code, but as a final test when you think your code is working. So you should be making sure your testing methodology is well defined and thought through. Okay, so because if you try to use the auto grader as a way of testing code, it's pretty difficult to figure out actually what's going on in some cases, right? So it's good to have tests. All right, any other administrivia questions? Kubi, are the Giants going to win the World Series? Yes, in 6. That's my prediction. Anything else? Maybe I'm being optimistic. Yeah. Yeah, so I wanted to apologize for the lateness of this. The reader got a late start getting things back to us, but hopefully everybody now has their feedback from the reader on Design Doc 1 in email, I think, right? She's emailing it now. That's why I let her have her laptop. So this was actually, unfortunately, the reader's fault. But we will hope to get everything back to you much sooner on Project 2.
They're going to whatever email you put when you register.
They're going to your registration email. Yeah, question?
The link to the midterm wants to be
Really? Okay, I will fix it right after class. That's funny. Are you going after the instructional computer, or try my homepage version of the website? By the way, that's a good idea. If you ever try the instructional version of the website and something doesn't seem right, try my version, because although I call mine a mirror, it's actually the primary version usually. So, and if it still doesn't work, well, I'll fix it anyway. We'll get it fixed. Any other questions? Has anybody actually been able to see the solutions ever? Yeah, so a few of you have found them. Okay, so they do exist. Ah. Oh, they're not on the main one. Okay, that's my bad. I'm sorry. I'll fix it. Okay. Good. Also, if you have any, I think they'll mention this in section. So in section, you hopefully get your midterms back. We have a policy of basically a week to submit written regrade requests. And also, if you have any regrade requests on your project design docs or something, submit those in writing as well and give them to your TA. Okay? And we'll handle. All right. Good. So one thing I did want to point out from the test. So monitors look like this, generally, a monitor-based program. You should have, hopefully, this pattern burned into your brain by now. You know, this idea that you grab a lock, you check some condition, you wait, in a while loop, you unlock. Then you do something that's been, so this is like an entry to the condition you're checking, and then you do something without the lock on, and then you grab the lock, you signal somebody who might be sleeping, and you unlock. And this was kind of a general pattern that we gave you guys. Okay, remember that? The reader's-writer's case was certainly like this, which you got to know and love on the exam. So we had a couple of folks that said, well, this can't work properly because you're accessing, we had a database in here, the database outside of the lock. And of course, the point of that was that the lock is the monitor that's guarding entrance to the database, not the lock is not guarding the database. So that was a distinction I wanted to make sure everybody got. Okay. The other thing is, once you learn a pattern like this, of course, what's a good thing to do on an exam is to push your knowledge a little bit. And so we broke the pattern on the exam. Did everybody catch the fact that we broke the pattern on the exam? Okay, a couple of people, when I said, why might you not want to use while, gave me an explanation of why they wanted to use while. Okay, now my assumption was you were going on a pattern which used while, and I was asking why not use while. Okay, now I just wanted to point out what the final code kind of looked like. This is a strange use of code, but it's not too bad. If you look at what we're doing, we're taking everything in order. If anybody's queued at all, then we queue people up front. And then there's a single person in the on-deck queue that sort of checks and sees whether they conflict with people that might be accessing. So for instance, if there's more than one person accessing the database and either I'm a write or there's a write going on, then I got to wait. Okay, and then when we exit this on-deck case, then we say, well, I'm going to the database. So there's one more accessing it. It's this type. And I'm going to now signal the wait queue up here. Why do I do that? Because this guy is only one person at a time, and this is purely checking conditions, and this guy is the entry queue. Okay? Now the question is, why don't we want a while statement here? Yeah. Yeah. The biggest problem with putting a while here is because we're relying in this code on this guy being FIFO. And therefore, if we do a while and we put him back on the queue, we just messed up our order. Okay, so here is a case where we're relying on a property, which, by the way, you don't normally get, unfortunately, with wait queues. But the property we're relying on is FIFO-ness, and therefore while is going to mess it up. There are a few other answers we gave partial credit for, but... and then finally, when you exit the database, notice the pattern back here. We had several people that forgot to acquire and release locks at the end before they accessed shared information. Okay, that's missing the pattern. And then here we sort of say, well, there's one less person in there, and we signal the on-deck queue. Okay, we also had a bunch of people who would do something like this. If on-deck greater than 0, on-deck queue.signal. Somebody tell me why that's not required? Go ahead. Yeah. If you signal and there's nobody there, it's ignored, right? So you don't have to. So there was a number of people who spent a bunch of code writing things like if on deck is greater than 0, then signal and so on. You just don't need to do that. But anyway, all right. I just wanted to point out the places in which the code we had you play with on the exam. Play is the wrong word. Think about on the exam was not matching the pattern. This was more about not matching the pattern than matching the pattern. And I encourage you to look at the solutions and really think it through, because who knows, there might be another problem like this on the final or something. I could see that happening. So it'd be good to make sure you fully understand this code. All right, are there any questions on this? All right. There are subtleties here too, like we signal up here instead of down here and so on, which is kind of interesting. So you should think this through. I would say make sure you understand every line of code in here, and then you know you're on good terms. Okay. Last thing I wanted to say is, can you get deadlock with a single monitor and lock? Yes. And I wanted to just, the simplest way to look at this is you just build semaphores with monitors. Here's a semaphore. Right? To do the P operation, you grab the lock and you say, well, if the X value is 0, I go to sleep, and I do that in a loop, and otherwise it's not 0, so I decrement it and I release. And then the way I do V is I acquire the lock, I increment the value, I signal anybody, one person who's waiting, and then I release. Okay? And once I built these, then I just build my circular dependence, thread 1, thread 2. There's a cyclic dependency deadlock. All right, everybody with me on that? Because I can build semaphores out of monitors, then I can do all the deadlocky stuff I introduced when I introduced deadlocks. Now, you don't have to do all this on the exam for the answer, but this is a general idea, which is just because you only have one lock in a monitor doesn't mean you can't screw up and get into some cyclic dependency on the condition variables. So, okay. And basically what you should remember is that monitors and semaphores are kind of, they're like Turing complete synchronizers or something. Each of them you can build with the other one, and therefore something you can do with one you can do with the other. Okay, by the way, I'm very much abusing the word Turing there, but that's okay. Okay, any questions on that? I did warn you that synchronization was the hardest concept in this class, and I have to say it takes many passes through to get comfortable with it. So I would take the time and do a few passes through and get comfortable. The fact that maybe none of this is obvious is completely understandable. It's hard to think about the first 12 times. The other thing that's kind of interesting about synchronization problems like this is I get the impression when people write a solution down, I realize it's high pressure and all that sort of stuff, but it's very easy to come up with one ordering of something and think it through and say, okay, I figured it out. And you never quite go that second step of mentally simulating something slightly more complicated. Okay, like not just a read followed by a write or a write followed by a read, but maybe a read-write-read or a write-read-write. And I think most of you that got hung up on your solutions to this actually didn't go that one last step of thinking write-read-write or read-write-read. So and this is a good debugging technique in general. So, okay, and I'm more than happy to spend long time explaining this to you guys in office hours or ask people in section, whatever, because we want to make sure everybody gets it. Okay? Any other questions? All right. So let's talk a little bit more about pages, and then we'll take a break. So now we've been talking pretty generically about pages, and we didn't really differentiate between processes. Okay? So if you have many processes in a system, how do you choose which ones get memory? Does every process get the same fraction? Okay? Or different fractions? Should we swap whole processes out? Rather than trying to have 100 processes all competing and swapping, maybe we should have 50 of them on the disk. Okay? Well, clearly each process has a minimum number. How big is the minimum? Say again? I would say the minimum is not the size of the code. It's much smaller than that. So that's a good question. I mean, that's a good thought. Let's explain why that might not be true. Because we've got demand paging, we don't actually have to have all of code into memory, right? Only the ones that we're using. So, and this is particularly useful, by the way, with modern, libraries that do windowing type stuff. There's huge chunks of stuff that your program never ever needs to use, and so why swap it in? So definitely not the size of the instructions, not the size of the stack, because you got the top of the stack is the thing you're using. Yeah, go ahead. Say again? So a program, well, so how about 6 or 2 pages? Okay. So how do we calculate that? Well, here's an example. So some complicated machine like the IBM 370, it turns out that you need 6 pages to handle the move. Okay, there's 2 pages for the from, 2 for the to, and the instruction itself might span 2 pages, so you need 2 pages for the instruction. Now, why do we need all 6 of these? Well, the point is that if we don't have those 6 paged in, we can't run that one instruction, and that thing doesn't make any forward progress. Okay, so when asking what's the minimum number of pages, and this is, by the way, a CISC machine, it's probably like 2, like 1 for the instruction, 1 for the data. Everybody with me on that? So that's how we got minimum. And minimum is kind of, the only way I know that I make forward progress at all is if one instruction can execute. If I can't even get one instruction to execute, then I got problems. I'm not making any progress. Okay? Now, obviously, this is not a great number to have for this program, right? Because it probably needs more than these 6 very rapidly. But certainly, if we want to make sure this program, for instance, in this case, could make some progress, we'd need at least 6, or 2 in the case of a RISC machine. So with that in mind, we can kind of ask, when we start pulling pages in for a process, where do we grab them from? And we have a couple of replacement scopes. One we'd call global and one we'd call local. So the global scope would say that when process A needs pages, it grabs them from anybody. So that would be like saying the clock algorithm really is the way I've described it to you, and you just grab the next page on the clock when you get a page fault. Local replacement is more that, a process has been given so many pages, and when it pages something in, it has to page one of its own pages out. Okay, and that actually seems, I mean, that's maybe more fair. I don't know, which one is more fair? Yeah. So local replacement favors programs that have smaller memory needs. Why is that? I see. So basically, good. So if we partition things equally, that was the first statement, and we do local replacement, then things that have small page requirements are really happy, and ones that have big ones are not. That's correct. The problem with global is sort of a flip side. If you've got a memory hog, then it basically will take out everybody, right? So this kind of local is a little more isolated than global. And which one do you think is normally used? Unfortunately, global is pretty common, right? This is why when you got a memory hog running and you try to click on some window, it takes forever to page the window back in, right? Yeah. You're asking, do we still need a core map with local mapping? Was that the question? Yes. That's the question. I would say yes, because it's possible that even in the case of local replacement, you've got shared pages. Yes. Good question. Yes.
Isn't global replacement sort of like even out in a way? If one process just takes out a page from another one, that same process will potentially need it and just take it from the one that just, it's sort of like it's just like three-way processing.
Yeah, I think your question is, doesn't the global one sort of self-adapt? Eventually, somebody who has a lot of pages tends to replace its own pages. Is that what you're asking? Yeah. I mean, I would say the nice part about a global replacement policy is really that it's more self-adaptive to the needs. It's all of the programs, but it's also more abusable. Yeah.
Does the process itself that needs another page get to select who it takes that page from?
So this is a great question. Does the process who's getting a new page get to say who it takes a page from? Usually no. Okay? And that extends even further. If it's going to replace one of its own pages, it usually doesn't get to say which one of its pages. So this is why, by the way, demand paging is frowned upon by people who think about operating systems of the future. Because really, virtual memory has some very bad properties to it, as you can see, which is, if I'm going to take a hit by swapping something out, I should at least be able to say which thing I'm going to take a hit on. And so that's why kind of in our research group, we're looking at new interfaces for virtual memory that let processes actually say what they want to replace. And these ideas have been around for a long time. They just haven't made them into real operating systems. Yeah?
Can't in most real operating systems request that pages not be swapped out?
So you can pin pages in many cases, but that process is usually of limited availability to user code because you can really abuse it badly. And so, you might allow a user process to pin a few of its pages, but not big chunks of them. So probably, yeah. Okay. So let's just look at a couple of allocation schemes here. So one is we could do equal allocation where everybody gets the same amount of memory. Probably a bad idea, right? Because not all processes are created equal. So if we had 100 physical frames, 5 processes, each gets 20. Okay. Another could be proportional allocation. So somehow, I don't know if people still read Animal Farm anymore, but in this case, some processes are more equal than others, right? So basically, we allocate according to the size of processes. So here, computation proceeds in the following way. If we have some size parameter for process P, we add up all the size parameters. We then use that to come up with a proportionality factor times the amount of memory, and that tells us how much memory each process gets. Okay? What's the big problem here? Yeah. Well, yeah, so what is S? Well, you tell me, what should S be? Pages it needs. Okay, how do we know what that is? Who tells us that number? I'm actually just asking you because it's a good question. Yeah, go ahead.
Well, I mean, I guess.
So proportional allocation sounds great on the face of it, but when you push on it a little bit, it's like, who tells you what S is? Yeah, it's the number that it really needs. Well, isn't that what sort of purely global allocation sort of does? Because you end up paging in what you need and paging out what you don't. But this seems like an attempt to do local allocation in a way that maybe is a little more fixed, but I don't know. What should we do with S? Go ahead. Yeah.
Let the user specify it for notification.
Yeah, so the obvious thing is let the user specify it. So what's wrong with that? Okay, this is users run wild, right? Yeah, go ahead.
We always do is just keep statistics of like last time we ran the program, we're going to run multiple times, and the next time we'll get close to some.
Yeah, so maybe we could take statistics of program use, but then again, there's ways of abusing that, right? You basically make sure that you touch as much of your memory as you possibly can, so therefore you really need it, right? Okay. Not obvious where S comes from. It's a great question. What about priority allocation? Those with higher priority get pages from those with lower priority. How about that? Does that make sense? Yeah. Where are priorities coming from? Well, that's a good question. Where did they come from when you guys did them? Priorities in your nachos system. Okay, but the processes got them from somewhere. User probably, right? So it's probably ultimately the person who started it says what the priorities are. So these are all fine schemes as long as, well, the equal allocation is a little questionable, but proportional and priority seem like great ideas as long as you've got good priorities and good sizes. But those are hard things to get well. And you could imagine maybe having some sort of machine learning thing that watches previous executions and tries to decide what's right. But it certainly isn't, let's take S and take the total amount of memory that process S allocates and use that in our proportionality computation, because anybody who links in a huge shared library suddenly has a big S whether or not they actually need the memory. Okay, so it's a little tricky. Okay, question? No. All right. So maybe we need some sort of adaptive scheme. So let's we'll do a couple more slides and then we'll break. So can we reduce capacity misses? So I just want to say this is a little bit of a side topic, but capacity misses are what again? What are capacity misses? Say again? Okay. Capacity misses come because we have no pages left, so everything we bring in, we have to kick something out, right? So can we dynamically change the number of pages per application to fix the capacity miss issue? Sure. That's basically a more general version of what I said earlier, where we're adapting the amount of memory we're going to allow a process to have dynamically. Okay? And what we'd like here is this idea that we find the right size. And how do we find the right size? Well, one is we look at page fall rate. So here's a typical application, and as I give it more pages, its fault rate goes down. And if what I want to do is somehow dynamically decide what the right size is, I pick an upper and a lower bound on page fault rate, and I make sure the application fits in there. If it's got too many page faults, it doesn't have enough memory. If it's got too few page faults, it's got too much memory. And therefore, I try to fit in this nice range, and that might be a way to right size the amount of memory we give it. It's kind of a dynamic algorithm where page fault rate is our metric. Okay? What if we don't have enough memory to adjust everybody to their ideal page fault rate? What happens? Yeah.
Pages allocated to each process and end of cycle. So the process gains a page but takes from the other, and then later on the process that lost a page might take it back.
Yeah, so basically we get stuck in this mode doing nothing but paging, right? And that leads to thrashing. So here's an interesting graph where as we add more and more processes, the amount of time the CPU is utilized starts rising to a point and then it suddenly drops. Can somebody explain to me why the utilization might rise as I add more processes? Now, utilization is a measurement of how often the processor is used. What fraction of time is it busy? Yeah.
Because you have more work to do certain processes do I/O.
Yes, great. This is an I/O effect, right? If you got processes doing I/O, then they're not always working. So as I add more processes, I'm better overlapping I/O and compute. That's great. Why does this fall off at some point? Yeah.
All the processes are waiting to use the disk, and so the CPU has to.
Yeah, not only are all the processes waiting for the disk, but the reason they're waiting for the disk is what?
They're just swapping.
Yeah, they're busy swapping in and out, right? So this is a very bad effect, very nonlinear. And you've all experienced this probably on instructional machines, right? You try to log in and do something. And so the word thrashing is basically a case when a process is busy swapping pages in and out and doing nothing else. And how do we detect thrashing? Yeah, we could look at CPU utilization. Yeah, what else? Hard drive activity. How about page faults per unit time? Hard drive activity is kind of the same thing. So what's the best response to thrashing? Yes?
We stop the duplication of processes.
We want to stop growing the number of processes. What else? Yeah. Okay, we might want to kill, if we kill a few processes, the rest will benefit. Yes. Now, unfortunately, the ones whose process you killed probably are not too happy. What else could we do? Who said suspend? Yeah. So we could find the ones that are causing the most trouble and swap them, actually, would be the right word, where we actually push them completely out. Okay? Yeah, go ahead. Could get a better computer? Yeah. All right, let's take a break. We'll come back and we'll talk more about thrashing. Right. So let's finish up this thrashing idea by seeing if we can quantify it a little bit more, and then we'll move on to some discussions of I/O. So you can imagine that a program has an access pattern. We've shown you something like this before, where we have execution time along the x-axis here, and which address is being touched is along the y-axis. All right, so fuzziness here represents actual things being accessed, and space is sort of addresses not being touched. Everybody with me on that? Now, you can imagine that if you look over time, okay, you can talk about, for a given slice of time, what are all the pages that were accessed? Okay, wasn't that a cool, there we go. So what's inside this bar is actually the set of addresses in that delta time period that were accessed. And furthermore, you could say, well, these are the pages that if they're not in memory, we're going to get page faults on and need to page in, right? So the working set, which is, again, in a given delta, which is the width of this fuchsia bar here, the pages that are accessed is the working set. Okay, it defines the minimum number of pages that actually have to be available to the process to avoid thrashing. Okay, now, not enough memory for the working set means you thrash. And at that point, it's maybe better to swap the process out and let somebody else get their full working set in memory than to actually waste time with the disk. Okay? Now, a working set model here, again, is sort of this notion that if you take all the addresses being accessed and you pick your delta, which we'll talk about picking delta in a second, you can say all the addresses in there are the working set at a given period of time, say T1, and there's a slightly different working set at T2. So in fact, typical programs actually work their way through sets of working sets. Okay, that's kind of, they have phases to them. Okay. So what is a good working set window? Well, 10,000 instructions, let's say, or something. So that you got to be careful, because if delta is too big, you sort of say, well, the working set is every address ever touched by the program. Not sure how useful that is, because we're trying to get some instantaneous behavior. If you make it too small, you end up with, basically, again, not enough information because you don't really know the global behavior. You want something that's basically more on the time scale of where paging might matter. So 10,000, 100,000, million instructions. So we can talk about the working set of sub I of process I, total set of pages in delta, and again, we can decide how to choose delta. And the total working set of everybody in memory is what? Well, you just sum the working sets of everybody. So this sum of the magnitude of the working sets basically says how much memory, what's the total demand that I have for a given set of processes running such that I don't thrash. Okay, and if I don't have enough memory to match D, then I'm going to thrash. And if I have more than D, then I won't thrash. Question, yeah.
We don't actually define the working set for a given process, right? That's kind of defined based on the process.
So, in some sense, you could say the working set is, as you mentioned, is defined dynamically by what the process is doing. On the other hand, we could, in principle, collect the working set, because we could just take the set of last set of page faults and kind of approximate what the working set really is and figure that out, right? But yeah, it is a dynamic number. And so if D is, the demand is greater than the amount of memory we thrash. So we could have a policy that if D is greater than memory, then we suspend and swap processes until D gets less than memory, and then we can get overall behaviors better. Now, when I say suspend or swap out processes, I don't mean kill. That was suggested earlier, but that'd probably annoy whoever got killed. It's more that what we do is we're putting them offline long enough to let the other things make progress, and then we'll bring them back in and let them make progress. So it's actually better to suspend something entirely, let other people make progress, and then bring them back than it is to try to interleave them at too fine a grain. Okay. Any questions on that? Yeah.
I had a question about the last slide. How does one collect that sort of data?
So the way you can collect this data is if you so you can kind of figure out which pages are paged in from a process, okay, because you can basically stop at any time and look at what its page table is, right? And so if you wanted to really collect a working set, then what you'd do is you'd have to keep track of the age of pages and try to throw out pages after a certain period of time, and then the working set will be the ones that are still in core. So you can kind of set up an experiment to collect the working set. So that's on a live system. If you're simulating, it's really easy because you just look at what accesses are being grabbed by the loads and stores. Okay? So what I was giving you is how you might do it on a live system, and it's clearly got some overhead to it, but it's plausible. Another question? Yeah, you could probably figure out a way to make nth chance give you working set. I hadn't thought through that, but it's plausible. Maybe. I'll grant you that as a possibility. Okay. Good. Any other questions? Okay. So what about compulsory misses? So the way we fix capacity misses is maybe we adapt automatically. So compulsory misses are pages that are pulled in the first time and haven't been pulled in ever before, or maybe after you swap something back in. So how could we improve compulsory misses? What's the default answer to that question always? Prefetch. Okay, so we could always prefetch. Another one is clustering. So here, you sort of, on a page fault, you actually bring in multiple pages around. So this is a form of prefetch around the page that was being paged in. What are we going after? We're going after spatial locality here, right? So we're saying, gee, if I pull this page in, maybe I want those others that are close to it. And this is actually done. Another thing which is not done, but it always seems like it could be a good idea, is when you go to swap somebody out, you figure out what their working set is, and before you start them running again, you swap in the whole working set. Okay, but this is, I don't know of any operating systems that do this. Okay. Questions? All right. So here's our summary on demand paging, and then we'll talk a bit about I/O before the end. So we talked about some replacement policies, which nobody actually uses, but are good base cases, FIFO, MIN, LRU. And then we talked about the clock algorithm as an approximation to LRU. The clock algorithm in all its many forms is used. We talked about nth chance as a variant of the clock algorithm. We talked about the second chance list algorithm, which is used in some, was certainly used in VAX VMS. We gave you the idea of working set, and we defined thrashing. Okay. So I'm going to switch gears for the last 10 minutes of class and talk a little bit about I/O, and that's going to be our next topic. Well, actually, let me stop right there to see if there are any other questions on paging before we put that aside. Any last questions? Nope? Okay. So far in this class, we're talking about managing CPU and memory. And I will tell you that a computer with only CPU and memory is a very boring computer, right? It's all the I/O devices that make things interesting. And so what about I/O? Well, I don't know, disembodied brains or something if you don't have it. So thousands of devices, everyone's slightly different. Okay, how do you standardize? Okay, so you got lots of computers, you got lots of phones, you got lots of storage devices. Everything's a little different. And remember that chaos I mentioned at the very beginning of the first lecture is where the operating system really helps us. It takes this bunch of different devices and somehow gives us a standardized interface so that the programmer doesn't have to care that he's storing data to a floppy disk, a hard disk, a USB drive, whatever, right? That question almost never comes into play as to how the programmer deals with it. Another thing that the operating system is going to need to deal with is the fact that devices are fundamentally unreliable. When we've been talking about CPU and memory have the advantage of being reasonably reliable. Okay? Things crash occasionally, but mostly memory's got ECC on it these days pretty much, and you don't lose too much of your memory, and the CPU is mostly working. The moment we go to I/O devices, all bets are off. Failure is the normal mode. Okay? And I hear some laughter on that, but believe it or not, failure is the normal mode, but there are techniques in play that help you not have to worry about failure. Okay, like disk drives have error correction codes, and networks retransmit and all that sort of stuff. So those failures which occur all the time don't bother you mostly until you actually lose a whole bunch of data, and then you're really annoyed, right? How many people have lost a bunch of data because they didn't back it up? Anybody admit to that? I even did that once or twice. So the other thing that's kind of interesting is devices are unpredictable. They don't give you things back in a well-defined period of time. If we talk about a hard drive, which we will, you may seek or not seek. Okay, and because that mechanical arm may get invoked or not, the variation in latency can be huge, factor of 2. Over the network, we all know that, right? The variation in latency to getting somewhere can vary a lot. It can be really fast sometimes and really slow other times. So somehow the operating system is going to have to deal with that. So what are some parameters to this problem? Okay, well, let's talk about a few things. So one thing is the device a byte device or a block device? Okay, is a disk drive a block device or a byte device? Block device. Why? Good. What does that mean, though? Because it's whole blocks at a time, right? I've talked about single byte at a time like keyboard. Can anybody give me any other block or byte devices? What's another byte device? Say again? Yeah, mouse. Good. How about another block device? Ethernet. Okay, why is that a block device? They're quantized in packets, but actually they're at the granularity of bytes if you're using TCP/IP, so that one's a little tricky to figure out. How about a USB flash storage device? Is that block or byte? How many people think that's a block device? It turns out that if you're using NAND flash, which is exactly what all the biggest ones are, they're actually block devices, believe it or not. So you might ask whether it's sequential or random. So in other words, do you have to get things in order, or can you get them completely randomly? Okay, random access. Are you going to access them via polling or interrupts? So this is a question. Do you wait for the device to interrupt you, or do you continually check the device? Okay. All right. So a modern I/O system is many things attached to a computer. Here's a little computer right here. Okay? And what's interesting is everything else, and this is an old set of buses now because PCI is kind of central, but you've probably got some bridge controller, then you got PCI bus, and then you've got other expansion buses, and then you got sub buses and SCSI buses and IDE buses for disk drives and all that sort of stuff, and then ultimately you've got networking. So what's kind of amazing is when you look at a real system, the CPU and the memory is this little piece, and everything else on the outside is where the complexity comes into play, and it gets very interesting. And the question is kind of how do I make sure the data comes in from where it's supposed to go, goes out to where it's supposed to go, and does so in a timely fashion and does so in a way that's not totally confused. Okay, that's complexity. And some of that is in the hardware, but a lot of that's in the operating system. And the other thing that's interesting is this is old data, but it gives the point. We've got everything from keyboards, which are at very low data rates, to buses that are running at gigabits and gigabytes per second. Okay, we've got gigabit Ethernet. So there's a huge variation, many orders of magnitude. So do we treat every device the same? Do we treat a really high-speed device the same as a really low-speed device? What do you think? Probably not, right? Probably some differences there. So what's the goal of an I/O system? Uniform interfaces, despite lots of devices that are different. Here's an interesting thing. Here's some code. Basically, we do a file open on dev something, read write. We go through it, and we fprint a bunch of stuff to it, and then we close. Notice that other than maybe what the word something actually is, you don't know anything about this device. This is a standardized piece of code that just works on a wide variety of devices. Okay? That's one of our goals, is uniform interface. Doesn't matter whether this is a disk drive or it's a or it's a USB drive, or it's a network. Okay, yeah, this probably wouldn't quite work for a network, but you get the point. All right, so some part of the operating system is giving us a standard interface. That's the device driver. No, we're not going to be designing device drivers in this class because that's a little bit too low level for nachos and also too low level for a class like this. But I will tell you a bit about what's in a device driver next time. So we're going to try to get a flavor for what's involved here, but can only scratch the surface. And if you're really interested, I'll point you. There are a number of books that have been out for a while on how Linux device drivers work, for instance. I can point you to a few of those for those that are really interested. Okay. Any questions so far? So there are actually kind of three standard interfaces that have shown up over the years. And in some sense, these are historical, but they're pretty useful. There are block devices, which are, as I mentioned, things like disk drives, tape drives, DVDs. You get data in blocks. You've got things, system calls like open, read, write, and seek. So you all implemented these system calls last time. You can either implement raw I/O where you don't have a file system, or in some cases you actually can look up names. And in some cases these block devices can be mapped right into memory, and you can read and write them through memory. Then there are character devices, okay, keyboards, mice, serial ports. Here there's typically just get and put are the system calls involved, but then usually libraries give you things like get line and parsing and stuff. And then finally, there are network devices, and this is, I would say, a pretty historical distinction from the other ones, but it is a completely separate type of device as far as most operating systems are concerned. And here we're talking about Ethernet, wireless, Bluetooth, any of those actual connections you make to the world. And most of these devices have what's called the sockets interface, and we'll talk about sockets. And basically what it does is a socket is an endpoint. You need two sockets, one on each machine, or maybe on the same machine. You connect them together, and poof, you got a stream. You write out in one side of the socket, and it comes out on the other side. Okay? And that's, what are these kind of devices used for? Well, they're used for pipes inside processes, streams, queues, mailboxes. TCP/IP is an example of this kind of protocol. All right, so these three device types are almost always in operating systems. Any questions about the types? Okay. So another thing that's kind of interesting is how do you get data? And this will be my last slide before we finish up. So we have either blocking interface, which is the one you're probably most used to, which is you go to do a read and your process goes to sleep until the data comes back. Is that the one you're most used to, right? That's a blocking interface. When you write, basically the write goes to sleep until the data is sent to the device. What are some alternatives? Well, one is what I'd call a non-blocking interface. So if blocking is the wait interface, a non-blocking is don't wait. And what the idea here is it returns really quickly from read or write, and it just gives you the count of bytes that were successfully transferred without ever waiting. So suppose you say read 100 bytes. It might say, well, I got 2. Here they are. Or read 100 bytes. Here's 0. Okay, so this one is about very quick, do what you can on the fly. The other type of interface is an asynchronous interface, which is the tell me later interface. And the idea here is read me 100 bytes. It returns right away. I'm doing stuff later, working on something else, and later it notifies me that, well, your 100 bytes are read. Here they are. Okay, so these are three kind of classes of interface. Any questions? Okay, so what we're going to do the next time is we're going to take and talk about sort of the different types of devices and the different types of timing interfaces, and we're going to try to put those together and talk about the way a device structure looks like in an operating system. Okay, so in conclusion, the final, we talked about the second chance list algorithm. We talked a bit about working sets. We talked about thrashing. And we started talking about I/O devices. The biggest thing to remember from our 10 minutes there is many different speeds, different access patterns, different access timing. And next time, we'll actually talk about how I/O controllers look and what the hardware is there that the operating system talks to. All right, go Giants. See you guys later.